Today we'll be doing the integral from 0 to infinity of 1 over x cubed plus 1 dx. And to start off, we will consider the function g of z equals 1 over z cubed plus 1. We could rewrite this as 1 over z plus 1 times z squared minus z plus 1. And we're going to set the denominator equal to 0. So that means that z plus 1 equals 0, and z squared minus z plus 1 is also equal to 0. Solving for z, we have z equals -1. And using the quadratic formula or completing the square, solving that trinomial, we have z, call this z naught, and z1 equals 1/2 plus I times the square root of 3 over 2. And z2 equals 1/2 minus I times the square root of 3 over 2. So visualizing this in the complex plane, -1 is right here, and 1/2 plus I times the square root of 3 over 2 will be somewhere here, and it'll be symmetric about right here, which is z2. And our contour will look something like this. It'll go from 0 to r, and then it's going to make this arc and then loop back around. So we have the integral over this contour of our g of z, which is 1 over z cubed plus 1 dz, will be the limit as r tends to positive infinity of the integral from 0 to r of 1 over x cubed plus 1 dx, plus the integral over this small arc, we'll call it a, of 1 over z cubed plus 1 dz, and then the integral from r to 0 of 1 over z cubed plus 1 dz. And the integral over this arc would end up going to 0, so we only have to worry about these two other secondary integrals. And notice as r approaches infinity, we will retrieve back the original integral. So we have the integral over this contour of 1 over z cubed plus 1 dz is the integral from 0 to infinity of 1 over x cubed plus 1 dx, plus the limit as r approaches infinity of the integral from r to 0 of 1 over z cubed plus 1 dz. And for this integral, we'll make a substitution. So we're going to let z equal x times e to the 2 pi I over 3. That means that dz equals e to the 2 pi I over 3 dx. So we're going to have a limit as r tends to positive infinity of the integral from r to 0, 1 over x times e to the 2 pi I over 3 cubed plus 1, and dz is e to the 2 pi I over 3 dx. So we have the limit as r tends to positive infinity of e to 2 pi I over 3, the integral from r to 0, 1 over x cubed times e to 2 pi I plus 1 dx. And e to 2 pi I would just end up being 1. So we have the limit as r tends to positive infinity of e to 2 pi I over 3, and the integral from r to 0 of 1 over x cubed plus 1 dx. So we have e to 2 pi I over 3, the integral from infinity to 0, 1 over x cubed plus 1 dx. And we can rewrite this as -e to 2 pi I over 3 but that's going to flip the bounds of integration. So you have the integral from 0 to infinity, 1 over x cubed plus 1 dx. So that's going to be equal to the limit as r approaches infinity of the integral from r to 0 of 1 over z cubed plus 1 dz. So we have the integral over this contour of 1 over z cubed plus 1 dz is the integral from 0 to infinity of 1 over x cubed plus 1. Then we're going to have a minus e to 2 pi I over 3. Integral from 0 to infinity 1 over x cubed plus 1 dx. Factoring out the integral, we have the integral from 0 to infinity of 1 over x cubed plus 1 dx times 1 minus e to 2 pi I over 3. And then multiplying both sides by 1 over 1 minus e to 2 pi over 3, we're going to get that the integral from 0 to infinity 1 over x cubed plus 1 dx equals 1 over 1 minus e to 2 pi I over 3, and then the integral over this contour of 1 over z cubed plus 1 dz. And we can evaluate this integral using the residue theorem. So we're going to have 1 over 1 minus e to 2 pi I over 3. And we're going to have times 2 pi I, the residue of 1 over z cubed plus 1 at z equals 1/2 plus I times the square root of 3 over 2. So from here, we're going to backtrack a little. And we said that 1 over z cubed plus 1 is the same thing as 1 over z plus 1 times z squared minus z plus 1. But we said that the poles for the trinomial was z1 is 1/2 plus I times the square root of 3 over 2. And z2 equals 1/2 minus I times the square root of 3 over 2. So this means that z squared minus z plus 1 can be factored into z minus 1/2 minus I times the square root of 3 over 2 times z minus 1/2 and then plus I times the square root of 3 over 2. So this means that 1 over z cubed plus 1 is 1 over z plus 1 times z minus 1/2 minus I times the square root of 3 over 2 times z minus 1/2 plus I times the square root of 3 over 2. So using this information, we have a 2 pi I over 1 minus e to 2 pi I over 3. The residue of 1 over z cubed plus 1 at z equals 1/2 plus I times the square root of 3 over 2. So evaluating this residue, we have a 2 pi I over 1 minus e to the 2 pi I over 3. And then we're going to have the limit as z approaches 1/2 plus I times the square root of 3 over 2 of, well, we're going to write z plus 1 times z minus 1/2 minus I times the square root of 3 over 2 times z minus 1/2 plus I times the square root of 3 over 2. And since it's a simple pole, we're going to multiply this by z minus 1/2 minus I times the square root of 3 over 2. And so what that does is it will end up canceling the whole. So we have a 2 pi I 1 minus e to 2 pi I over 3. And the limit as z approaches 1/2 plus I times the square root of 3 over 2 of 1 over z plus 1 times z minus 1/2 plus I times the square root of 3 over 2. And evaluating that limit, we're going to have a 2 pi I 1 divided by 1 minus e to the 2 pi I over 3 times 1 over 1/2 plus I times the square root of 3 over 2 plus 1, but I could rewrite this as 2 over 2. And then we're going to have a 1/2 plus I times the square root of 3 over 2 minus 1/2 plus I times the square root of 3 over 2. So we have this, and the 1/2s cancel here, and 1/2 plus 1 will be 3/2. So we have 2 pi I over 1 minus e to 2 pi I over 3 times 1 over 3/2 plus I times the square root of 3 over 2, and I square root of 3 over 2 plus I times the square root of 3 over 2 would just be I times the square root of 3. But as you could see, these i's end up canceling, and we can rewrite this as 4 pi over 1 minus e to 2 pi I over 3 times 1 over the square root of 3 times 3 plus I times the square root of 3. So we have a 4 pi over square root of 3 times 1 minus e to the 2 pi I over 3, and then times 3 plus I times the square root of 3. So this 1 minus e to the 2 pi over 3 factor is the same thing as 1 minus the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3 using Euler's formula. So we're going to have a 1 minus cosine of 2 pi over 3 is negative 1/2 plus I sine of 2 pi over 3 is positive the square root of 3 over 2. So we have a 1 plus 1/2 minus I times the square root of 3 over 2, which is 3/2 minus I times the square root of 3 over 2. So you have the integral from 0 to infinity 1 over x cubed plus 1 dx equals 4 pi over square root of 3 times 3/2 minus I times the square root of 3 over 2, and times 3 plus I times the square root of 3. We can rewrite this as 8 pi over the square root of 3 times 3 minus I times the square root of 3, and then times 3 plus I times the square root of 3. So now all that's left over is to multiply these complex numbers. So 3 minus I times the square root of 3 times 3 plus I times the square root of 3. So we're going to have a 9 plus 3I times the square root of 3 minus 3I times the square root of 3 minus I squared times the square root of 3 squared. The imaginary parts cancel when we have a 9 minus -1, and the square root of 3 squared is just positive 3. So we're going to have a 9 plus 3, and that's going to be 12. So we have the integral from 0 to infinity 1 over x cubed plus 1 dx equals 8 pi over the square root of 3 times 12. But we could simplify this into 8 is 4 times 2, and 12 is 4 times 3. So 4 times 3, and the 4's cancel. So now we could say that therefore the integral from 0 to infinity 1 over x cubed plus 1 dx is equal to 2 pi over 3 times the square root of 3. And so this is the final result to the desired integral. Thank you very much for watching.